what I'm going to talk about is a way to solve the polynuclear growth model. I'm going to describe what that is. So there's not going to be any vertex models in my talk. Maybe very far in the back there's some, but of course, I mean, the title of the conference is something like probabilistic and algebraic aspects of integrability. So I want to focus in one direction in the probabilistic part. Okay, but let me get started. Okay, so I will start by just describing this this model. So this is called the polynuclear growth model. It's a growth model that takes place in. Okay, so the space is the reals and the heights are all integer valued. Okay, so you should think of a. Oops. You should think of an interface of this sort, and the rules are the following. So you have these little constant islands, okay, and they expand outwards at speed 1, okay, in both directions. So every down jump moves to the right at speed 1 deterministically. Every left jump moves to the left. Sorry, every down jump. I'm saying it wrong. So down jumps move to the left, up jumps move to the left, and down jumps move to the right. Okay, everything at speed 1 deterministically. Okay, so on this part there's no randomness. Okay, now the randomness of the problem is the following. So at the times or at the space-time points of Poisson point process of rate 2, so basically uniformly in space and time at some rate, you have nucleations, and a nucleation is just a little island that pops up on top of a certain given point, and then once you get this island, it starts spreading out. Okay, so those are the rules. There's one more thing I have to say, which is what happens when you have two islands sort of coming into each other, and all that happens is that they merge, right? So for instance, here, those two are just about to merge, and when they merge, they just sort of continue flat for the rest of time, okay? So this was introduced.
Why rate 1 and why rate 2? Sorry.
Why rate 2? Because it just makes life seem, it's just too, I mean, it's a scaling choice that makes some formulas nicer and some identifications later nicer. Of course, it could be anything, okay? Okay, so this was introduced as a simple model for a growing crystal, okay? And it has been studied I mean, at various times quite deeply, and I'm gonna say some things about that. There's one thing I want to say, I'm gonna come back to this a little bit later, I won't show it, but it may not be surprising that an invariant measure for the process, or sort of an invariant measure, modulo the absolute height, is given by independent Poisson processes up and down, okay? So you just throw your favorite Poisson processes of up jumps and down jumps, and this is gonna be conserved by the dynamics, okay? So this is gonna play a role later on. Okay, so I'll show a simulation. So for some reason, I have to go out of full screen. Okay, so this is a simulation just for you to have an idea. This is how the thing moves. The dots on the bottom are it's just a space-time Poisson process where the nucleations are happening, and this is what you see. So this simulation is due to Patrick Ferrari. It's among a list of simulations of processes of this sort that he has in his website. Okay, and of course you may expect that there's some dependence on the initial condition. So here's a different initial condition. Okay, so I can't pause this, but this initial condition, you can think of it as follows. There's a single site at the origin that's spreading initially, and there's just nothing on top, on the sides, okay? So the height here starts at, you can think of minus infinity, okay? So if you have nucleations on that part, you're gonna see nothing, because they just go to minus infinity. And you can see now that the geometry is very different, right? You have this sort of curved shape, advancing in time. But anyway, you might be interested in studying the fluctuations and that sort of thing. Okay, is the definition of the model clear? Good. Okay, so this is actually a very old model. It has been studied in many guises. So here's one way to see it. So this model is equivalent to something called last passage percolation, which I don't think we have heard of in this conference. So here's the idea. So I'm gonna describe it first only for the narrow wedge initial condition. The narrow wedge initial condition is this initial condition that I showed you in the last simulation, where you have 0 at the origin and minus infinity everywhere else. Okay, so I'm looking at this sort of light cone where I look at these nucleations, and then well, you see what's going on here. Every time I have a nucleation, I have a little island that's spreading outwards, and whenever two islands meet, they just merge. Okay. And then just by counting how many lines you crossed, and we have seen this in other talks, you can define a height function. Okay, and here I'm drawing the height function that's associated to this. Okay, and now if you think about it for a moment, if I want to know what's the height, let's say at this point, then the height corresponds exactly to the following problem. The problem is to find the longest path. So longest here means counting how many of these sort of blue cookies I eat on the way, and I want to go along this path. My paths have to be Lipschitz of at most constant 1. Okay, so they have to go between minus 45 and 45 degrees. Okay, and I look at the longest one I can get to go from this point to that point. Okay, and if you think about it, that's exactly what's happening when I define this height function. Okay, so this is an alternative way of defining the model as last passage percolation. Okay, here's another one, which will be probably familiar to many of you. So with this geometry, with the initial condition given as this narrow edge initial condition, this is equivalent, at least if I look at, at the one-point distribution, to the problem of the longest increasing subsequence. Okay, and all you have to do here is you sort of turn your head 45 degrees. You look at these dots, and then the relative order of these dots defines a permutation. The permutation has length, which is random. Okay, so it's a Poissonized random permutation, and it's actually it corresponds to the area of this square times 2 because of this rate 2. So you can compute it. That gives you t squared. And then since this is Poisson, okay, so it's basically uniform in space. The permutation you get is uniform. Okay. So in fact, this height here corresponds to the length of the longest increasing subsequence in your permutation. Okay, and that's a very famous problem. And it was famously shown by Bagdieff and Johansen, I guess 25 years ago, more or less, that this height of the longest increasing subsequence converges to a Tracy-Williams GUE distribution. Okay, so in particular, this tells me that this height for the PNG model goes to a Tracy-Williams GUE. Okay, and the scaling is this usual sort of 1, 2, 3 scaling. In this case, we don't see the 2 yet, but the fluctuations are of size t to the 1/3. Okay, how about more general initial conditions? Can I still recover them from last passage percolation? And the answer is yes, I can. And the way to do it is that if you want to, now imagine that this blue line on the bottom is your initial condition. Okay, so if you want to compute the height function at the top, what you do is you look at all possible paths from x down to times 0. Okay, and you see how many cookies you collect, and you add the initial condition at the bottom. Okay, and now you optimize over that. And that gives you exactly the height function at a later time. Okay, so this is the usual way to put an initial condition or a boundary condition on a last passage percolation model or a polymer model. So you just have to solve this variational problem. Okay, so a little bit more of history about this. So I just told you that if you look at the height function at the origin, and it could be at any point really, and you compute the scaling limit, by this Bagdieff-Johansen result, you get a Tracy-Williams GUE distribution. You can also study the scaling limit of the whole process, say near the origin. Okay? And in this case, it's known that this converges to the RE2 process. Okay? It's the RE2 process minus a parabola. Okay, so the parabola is coming from this macroscopic shape that you're seeing. But when you look at the fluctuations, they're given by this RE2 process, which is a stochastic process. It has also shown up in some other lectures. But in particular, it has it's stationary, and all its marginals are Tracy-Williams GUE. Okay? So this was proved by Prahofer and Spohn. This is really the paper where the series 2 process was first defined, and then in a stronger sense by Johansson, also around 20 years ago. And then in the flat case, it can also be, so the flat case is the first simulation I showed you, where you start with a flat interface. It's known, and this is maybe a little bit of a longer history, but still it's known that the one-point distributions are given now by Tracy-Whittam GOE, and the whole scaling limit corresponds to something called the ARE1 process. Okay, so that was, in this version, proved by Alexei and Tomohiro, together with Patrick Ferrari, now around 15 years ago. Okay, so what I want to do today is show you some formulas for general initial conditions. So what happens if I now want to just not do just these two, but just a general choice of initial condition. Okay, and I'm gonna now show you the formula. Okay, it has some ingredients that I have to introduce. And I want to show you a proof of the formula, okay? A sketch of the proof, to try to understand what's going on with this type of formulas. Okay, so in the next slide, I'm gonna show you the formula, but first I need some ingredients just to describe the formula, okay? So the ingredients are relatively simple. So first, some notation. I just introduced these discrete difference operators, so this nabla or grad or whatever, it's just a symmetric discrete difference operator of first order, and this is the second order version of that, okay? So these are operators acting in the discrete variable, okay? So this is all discrete differences. And then I'm going to introduce a specific random walk, so this is just a simple symmetric random walk jumping up or down at rate 1, okay? And I should make two comments here. So number one, this delta here is actually the generator of that random walk, okay? Because the random walk is jumping to two sides at rate 1. And the other comment I want to make is that you should think of this random walk as having to do with the invariant measure of the process, right? So the invariant measure of the process, at least for the height differences, is given by ups and downs at rate 1, which is exactly what this random walk is doing. Okay, now I'm going to fix some initial condition for PNG. So any reasonable, so more technically it has to be upper semi-continuous, but any reasonable initial profile you like. And the last ingredient I need is something I'm going to call this heat kernel, okay? So the heat kernel is the following thing. So I'm just looking at my random walk, and I look at what is the probability that my random walk between two given times A and B, it goes from U to V, two prescribed points. But I also ask, what is the probability that my random walk does that, and it also goes below this profile H that I fixed, okay? So it's just a given kernel, okay? Okay, so those are my ingredients. And with this, I'm going to show you the formula. There's this is just a technicality, but it's going to show up in the results. So I introduce a certain profile R0, and this R0 it's given by this supremum over the light cone of the initial condition. But the way you should think about R0 is that R0 is exactly the height function you get when you turn off the creations. So you just have these islands expanding, but there's no new creations, okay? So this is the dynamics without any randomness. And one thing to notice is that if I define that, then my height function is always bounded below by these dynamics without creations, right? Because it's always moving up. So if I have no creations, I'm just sort of making it smaller. So this is just a lower bound for the evolution of my height function. Okay. So given these ingredients, here's the formula. I forgot to say at the beginning, but all of what I'm talking comes from joint works with Jeremy Coistel and with Konstantin Metetsky in different subsets. So the formula is the following. So again, I take a general initial condition, this H0, and I ask, so for now I'm just going to look at the 1 point case. So what is the probability starting from H0 that the height at some point x is less than some given parameter r? And it's given by a Fredholm determinant, okay? So this height appears here as saying that the Fredholm determinant is computed on the integers above R. And this is the kernel, okay? So the kernel is quite simple in terms of what I just described. So the interesting part is this hit probability of going from some point to some other point and going below the initial condition. Okay, and it's surrounded by these operators e to the 2t grad minus t delta, and then a similar thing on the left. Okay, so there's more than one way to think about these two. So one way is simply these are basically the semigroups associated to this, at least in this case, it's just the semigroup associated to that generator. Okay, so they're just kernels satisfying these differential relations, but actually you can compute them explicitly, and they have a contour integral representation, which I wrote there, and they also have a representation in terms of Bessel functions. Okay, so it's completely explicit, but they do satisfy these differential relations.
You're supposed to be conjugating by this green stuff, because they're not the same on both.
I am not, yeah, that's a good observation. It's not a typo. I am not conjugating. Okay, so I'm conjugating in one variable, but not in the other one. And the way you should think about this is the following. So this hit probability involves a random walk moving for time 2t. So if I was just looking at the free probability, that would be just the semigroup associated to the walk. So it would give me e to the 2t delta. And then I'm sort of undoing that on the sides. Okay? So there's some, if you sum things in t, it all sums to 0 somehow. Okay, in terms of okay, I don't know, if you just count variables somehow. Okay, so this is the formula. Okay? So notice what happened. I look at the initial, I have a certain initial condition, and I want to ask what is the probability that I'm below a certain level when I start at that initial condition. And that's given as a Fredholm determinant of a kernel that's constructed from a random walk going below the initial condition. So there's some sort of reversal going on here. So the initial condition became the final condition that this random walk has to hit. And there's also a natural question, perhaps, which is like, what does this walk have to do with the problem? And of course, the relation of this walk with the problem is that this walk is essentially the invariant measure for the problem. Okay? So what I want to do today is to show you the proof, show you a sketch of the proof of this result, where those ingredients are the key ingredients. Okay?
Sorry, this is just a 1 point?
This is one point. Okay, actually, I was just switching to the next part of the slide, which is that there's multi-point versions of this formula, and they're analogous. So I'm just sticking to the 1 point mostly because it's simpler for exposition. But if you want to do a multi-point case, so it's still fixed time, but now several points. And I ask what is the probability that I'm below certain levels at certain points. The kernel is very similar. So now this is an extended kernel, just as you see sometimes in random matrix theory. So this extended kernel now is computed on a direct sum of n copies of L2. And it's constructed in pretty much the same way. Okay? It's just that instead of going from this hit probability, instead of going from x minus t to x plus t, it goes from xi minus t to xj plus t on the ij block. Okay? So the proof that I'm going to show is essentially the same for the multi-point case. So I'm just going to stick with the 1 point case, which is simpler. This looks like, if you, some of you or many of you have seen talks about these sort of formulas before, so it may not look so strange, but some of you possibly have not. So let me show you an example where you can compute everything explicitly, okay? Because this hit probability may look complicated. But so let's take this basic case of the narrow wedge initial condition. Okay? So in the narrow wedge initial condition, what you have is basically you have an initial condition which is 0 here and minus infinity everywhere else. So if I want my walk, say, to start at u, and end at V. And I want to compute the probability that my walk goes from U to V and it ever goes below, I mean, it ever hits the hypograph of this function. There's only one way in which it can do it, right? My walk has to go below the origin at time 0 and then go there, right? Because everything else is minus infinity. So this kernel here simplifies considerably, and all you get is just like a projection below 0 at the origin. And now everything is explicit, and if you compute, what you get is the Bessel kernel. Okay, just by computing the convolution of this against that, which is given by Bessel functions, against this projection on the negatives. Okay, so that's a computation. You get the Bessel kernel, and this is the kernel that arose already in earlier works for the narrow wedge initial condition. So at least in this case, it's very simple. Okay. The other case, the flat case, is also not so hard to compute because computing the probability that a random walk goes below a constant line, this is a symmetric random walk, so you can do it using the reflection principle. And you can also get formulas, okay? And you also do recover the older formulas. Okay. So let me now try to start explaining the proof, okay? Okay, so there's at least two ways in which one can get this formula. The first way we got it is not through the proof that I'm going to show you, but instead we got it as the scaling limit of a similar formula for discrete time T-sub with parallel update. Okay, so it's similar to, so Leo was talking about discrete time T-sub with sequential update. This is a version with parallel update. I won't go into the details, but essentially there's a way to take a scaling limit of this discrete time T-sub with parallel update that gives you exactly this polynuclear growth model. Okay, and the picture is here. So you have your T-sub particles around here. Then you have the height function, which, so suppose this initial condition here looks more or less flat in the sense that I have particle hole, particle hole, particle hole, except for a couple of perturbations here. Okay, and the perturbations that I have produce this either upwards jump or downwards jump, and then if you scale things correctly, these down jumps and these left jumps move outwards, and you can recover the polynuclear growth model. Okay, so if you have a formula for parallel T-sub, then you get a formula, if you take the correct scaling limit, you get a formula for this PNG process. And actually, formulas for T-sub had been obtained before, so they can be obtained through a method that has come to have the name of Bayes normalization, which was first introduced, again, maybe like 20 years ago, a bit less, by Tomohiro and Alexei and Patrick Ferrari and Prahofer, I guess, in a series of papers, which it gives you an explicit kernel, which can later be solved explicitly and give you explicit formulas. Okay? So that's not what I want to do now, because that's an algebraic approach, if you want, and you get formulas, but it's not entirely clear where they came from, at least if you just care about the probabilistic aspect. So what I want to do is an alternative proof, which is I'm going to check so I'm going to cheat a little bit if you want. So I'm given the formula, and now I'm going to check that the formula works. And the way to check that the formula works is to check that my formula satisfies the backward equation for the Markov process. Okay? So I have to check. So I'm going to define a function f, which is given by my candidate Fredholm determinant. Okay, and I'm going to check that if I differentiate this function in time, I get the same as the generator of the process applied to my function. Okay? There's a technicality here that I'm doing everything above this sort of deterministic growth. Okay? But let's just ignore that. Okay? Okay, so this is what I have to check. I have to check that the derivative equals applied to a function equals the generator applied to a function. I need to also check the initial condition. And of course, there's something I'm not saying here. I need some uniqueness, right? Because just to check that essentially that this equation has a unique solution, we are in a very sort of abstract space. So this is not the usual space where you do Markov process theory, but you can check that there's a unique solution. So once you check this, this gives you a proof of the formula. Okay? So what is L? I'm going to say what L is in the next slide. L is the generator of the process, okay? And it's acting on the initial condition. That's how things work when you look at the backward equation, okay? So this L here, it's the generator of this evolving height function. So the height function is the variable, and it's really acting on the initial condition. Okay, there's one part here which is very easy to, I won't really do it, but this is the proof. The initial data is very easy to do because essentially you have this heating probability, and remember that the heating probability went from x minus t to x plus t. So when t becomes 0, it's a heating probability going from x to x. So again, things, a little bit like in the narrow wedge example, things get much simpler very quickly, and you get a Fredholm determinant of essentially the identity minus a diagonal matrix which has ones and zeros, and it gives you exactly what you want, okay? So this is really very simple. The initial condition is not an issue. So what I need to do is to show this. So let me try you an idea of how this is proved. Okay, so I won't go into like the analytical details, but just to fix ideas, my state space, the state space for my process, is a space of upper semi-continuous functions. It just means that, and this is not going to be important for us, but it just means that I choose to close my height function at the discontinuities from above instead of from below. Okay, that's just a choice. And it's endowed with the Hausdorff topology on the hypographs of these things. But again, I won't really get into that. Because actually, this is a complicated state space. It's a state space of jump processes, if you want, and I have to apply my generator on that. It's a little bit of a nuisance. So it turns out to be better to go to an alternative representation where instead of looking at the height function, what I do is I just look at configurations of up jumps and down jumps, okay? Like here. So I have pluses, which are up jumps, minuses, which are down jumps, and these pluses and minuses move outwards in the correct directions, okay? So that gives me the relative height differences of my process. And then to really define the height function, all I need is to fix the height at one position, right? So let's say the origin. So I can change my state space from h, this height function, to this collection of an absolute height, and then the positions of the jumps and the signs of the jumps, okay? And this is an equivalence. So that's the state space where I want to work. To be honest, we will completely forget about the absolute height. Okay, so this is something I won't get into, but essentially throughout the proof, the absolute height plays no role. Okay, so I'm only gonna worry about the pluses and minuses moving in either to the right or to the left. Okay, you can convince yourself through the proof that the absolute height does not make any difference. Okay, so now I have to tell you what's the generator. Okay, and again, I will not really need the generator very much. Let me just show you quickly how it's defined. Essentially, just the structural form is going to play a role here. Okay, so the generator has two pieces. And now I'm going to talk about the generator only for the pluses and the minuses. I won't worry about the absolute height. So the pluses and the minuses move in different directions. Okay, so that gives you just these first order derivatives. Okay, that's what corresponds to, say, just a drifting particle. Okay, so you just get the derivative, and then you get the sign in front, which tells you whether the plus or the minus is moving to the right or to the left. Okay, and then there's the creation part. Okay, and the creation part I just write as you would expect. So if I want to apply the generator to a function of the creation part, what I do is I integrate over all possible positions. Okay. And what I do is I simply introduce a jump at a given site, right? But if I introduce a jump at a given site, it means that I put a plus and a minus together, okay? So I just introduce I have this sort of creation operator of a plus minus at a given site, and that represents the creations in my process. There's one more thing one has to worry about, which is these annihilations. Okay, when two things come together, And the way to do it is you don't put it in the generator itself, you put it in the states, in the domain of the generator. So you have to ask that the functions which you consider have a certain continuity, so that if I see let's see if I get it right, yeah. If I see a minus coming from here and a plus coming from here, and I take the limit as they get together, they just disappear, and I get the same as the function without those two, okay? So I will not use that, but it's something that has to be taken into account. Okay, so again, what's important here is just the structural form of these generators. And now let's move on to the proof. Okay, so okay. First of all, what do I have to do? I have to show that dtk equals the generator applied to k. So let me first compute dtk. Okay, dtk is very easy because you're differentiating a determinant, and when you differentiate a determinant, you get essentially the determinant times a trace. Okay, so this is the usual formula for derivatives of a determinant. Okay, so basically I get this formula in terms of the trace, and it involves the derivative of my kernel. And remember, the kernel is very explicit, so I can try to compute derivatives. I will do that later. Okay, what happens with the right-hand side? So now I have the generator applied to the determinant, and that's a complicated thing. Okay, but it actually turns out not to be so complicated, because remember, it has two pieces. It has the deterministic part, and it has this creation part. The deterministic part is just a differential operator. So just for the same reason, it goes inside in the same way. Okay, so you just if you had L det here, it would go inside and give you L det applied to the kernel. And then you have the creation part. Okay, that's not a differential operator. This is the part that involves, let me go back, it involves this integral of these differences of f with this creation operator inside. And here you have to check something, and what you check is that when you apply this creation operator to the kernel, it gives you a rank 1 perturbation of the kernel. Okay? This maybe not so surprising, because all I'm doing is I'm computing the probability that my walk goes from some place to some other place, and then I'm adding a single jump here. Okay? So I'm adding one more possibility for the walk to go below, which is, okay, maybe I had gone through this position, and before the creation, I had not gone below the height function, but now I am going below the height function. Okay? So if you do a computation, that gives you a rank 1 perturbation. And then there's this nice fact that for rank 1 perturbations, it's really an integral of rank 1 perturbations, but the integral, of course, it's linear, so it won't make a difference. And then there's this nice fact that for a rank 1 perturbation, the same algebraic structure arises. So if I compute essentially an operator which is giving me the kernel minus a rank 1 perturbation of the kernel, everything goes inside the determinant in exactly the same way. So quite amazingly, what you need to prove the equality that you need for this backward equation is the equality at the level. So you wanted the equality at the level of the determinants, and of course determinants are not linear, but due to the structure of these operators, everything goes inside. Okay, and now I only have to show the equality of this. Of the derivative applied to a kernel and the generator applied to a kernel. Okay? And okay, maybe now one is happy because you see there's a chance, right? Now everything is explicit, and maybe I have a chance of computing it. So let me show you how it's done. So maybe it's a good time to stop to see if there's any questions. I know it's a bit early to try to do proofs, but this is the most computational part, maybe. Okay. So, well, maybe this is the most computational part. But this is easy. Okay. The left-hand side I can compute very easily, okay? Because I have to differentiate the kernel. The kernel was explicit. I can write it in this form, okay? So I have three factors, the two black factors and the green factor. If I compute the derivatives of the black factors, it gives me this grad applied to k on the right and the left. And then there's an additional part, which is this green part, and you can check that that gives you 0. Okay, that's not completely trivial, but it works. And the reason is what I was saying before after Rick's question, which is that essentially this is like applying the generator for time, sorry, the semigroup for time 2t. And you have minus t here and minus t there, and if you put everything together and you put yourself in the right position, then this is 0. Okay? So the derivative of the kernel is just the commutator, it's 2 times, -2 the commutator of this graph with the kernel. Okay, this is just a computation. So now we're supposed to see that applying the generator to this is the same. Okay. Okay, so my claim is that this follows from just 2 probabilistic ingredients plus a computation which I'm not going to make. So the first ingredient is the fact that these independent Poisson processes are invariant for the PNG dynamics. Or if you want to think of it, basically the random walk is invariant for PNG. I'm going to use that. Okay. But there's several ways to show that. One way to show it is to notice that a product Bernoulli measure is invariant for parallel T-set. And then you take a scaling limit of that, and what you get is ups and downs as Poisson point processes. So that's the first ingredient. Okay? Here's the second ingredient. So it's a certain skew time, we call it a skew time reversibility process, property. And it's given as follows. Okay, so remember this construction. Okay, that if I want to look at the height function, I can think of the height function as this variational problem on this Poisson environment. So here's a simple property that follows out of that, and the property is the following. If I start, and I'm trying to represent it in that picture, but the proof is essentially the picture. If you start from a certain profile G, and you want to ask, what is the probability that my height at a later time goes above a given profile F? That probability is exactly the same as the probability starting from F, and now you follow the same process but backwards in time or down, and you ask, what is the probability that I end up below G? Okay? And I mean, you can work out the proof basically from the picture. Okay? So actually this is a duality statement. It's pretty much in the spirit of the duality relations which we saw yesterday. And in particular, I'm just showing this because this gives you a way to prove it, but in particular, if I now compute derivatives of this and evaluate at t equals 0, it gives me a relation at the level of generators. Okay? So it tells me, and this really looks like the type of thing we were seeing yesterday, if I apply the generator on this initial condition, on this indicator function that I go above, it gives me the same as applying the generator of the backwards process, which happens to be the adjoint generator, to the final condition. Okay? So again, it's the same sort of duality that we were seeing yesterday. And it really follows from just this representation of PNG in terms of the Poisson environment. Okay? So this is a special property of PNG. It's not only a property of PNG. Same sort of duality works for TASEP, say, but as far as I know, not for ASEP. Okay? So it's something special about this model. Okay. And what I'm saying there is, this basically I'm taking 1 minus that. Okay, so if I look at the indicator function that G is above F, I can turn that into the indicator function that G goes below F, okay, which is just 1 minus that. Okay, so I essentially have everything I need to show you the proof. So okay, I need to compute the generator applied to K, okay? So that's the generator applied to my function. So that's a typo, H0 should be H, doesn't make much of a difference. Okay, now all of these things on the sides don't depend on H, so I can just take the generator inside. Okay? And now, okay, we don't really need to go through the notation here, but essentially all I'm doing is the following. I'm saying, okay, I want to compute the probability. Right, I want to apply L to the probability, to this probability. This is the probability that my random walk goes below the function. Okay? So I can write that as the expectation of the indicator that the random walk goes below the function. Right? That's easy. Well, and I have this extra indicator function which tells me that the walk has to start at some point and end at some point. So I'm going to leave that aside for a moment. Okay? So now I have my generator here, L. It goes inside the expectation and it hits this indicator function. And now I can use my reversibility or duality or whatever you want to call it. L applied to H is the same as L star applied to G. Okay? And now you notice the following thing. If I didn't have this indicator function here, if I just had the expectation of the generator applied to this thing, I am computing an expectation with respect to the invariant measure. Okay? And the definition, if you want, of an invariant measure for continuous time Markov processes is that if I integrate the generator applied to some function against the invariant measure, I get 0. And that's essentially what I'm doing. Of course, I have this boundary condition here. But forgetting that, that's exactly what I'm doing. I have the generator applied to a function, then integrated against the invariant measure. Okay? So this should be 0. If I didn't have this boundary condition, I would get exactly 0. Okay? But I do have the boundary condition, so all I have to do is, well, I sort of do some sort of integration by parts. So I write this as the generator applied to the whole thing minus some leftover thing. Okay? Now this part is 0 because of what I just said, expectation of generator applied to the whole thing. And I get some extra term. And now I claim that, okay, so this vanishes. And I claim that this extra term here is easy. Why is it easy? Well, you have to compute. But now it's the generator applied to a very simple function. It's just that the walk starts at some point and ends at some other point. Okay? So you can just compute. You compute. You get this. Okay? It's just basically combinations of starting one above or ending one above or one below, or ending one above or one below. And when you put everything together, you get exactly the equation you were looking for. Okay? So that's the proof. And it essentially follows from these two facts. I mean, it shows you that this kernel is built out of this invariant measure, and it works thanks to this duality relation for PNG. Okay, so in the time that I have, in the time that I have left, I want to talk briefly about things one can do with formulas such as this, okay, and going a little bit back to integrability. So very quickly, this PNG process was known to be integrable, at least in some cases, for a long time. So here's a statement, and this statement goes back to, well, maybe a couple of papers, but in particular, a paper at the beginning of the century by Alexei, where you can get that the one-point distribution in this narrow wedge case, you can write in terms of a discrete Pareto-2 equation. Okay, so you can think of this as an analog of the usual Pareto-2 representation for a Tracy-Whittem GUE. And there's also a version for the flat initial condition, the two initial conditions that I showed you. It's more complicated. It's not really written down explicitly, but it follows from these two papers of Bike and Rains and Bike. Okay, so there's these Pareto representations. And I want to ask myself the question, can I do something for general initial condition? Is there some integrability still in the case of general initial condition? And the answer is that yes, there is. So essentially, what we have is that these one-point distributions are given by a Fredholm determinant of a kernel, and the kernel, basically from the proof that I was showing you, the evolution that governs this kernel is linear. Okay? So if you differentiate the kernel in time, you get this commutator. If you differentiate it in space, you get this other commutator. Okay? So somehow the formula linearizes the evolution of the kernel. And this is the usual thing you see sometimes in integrability, that you have a linear evolution, and then in this case it's being mapped through the Fredholm determinant to give you the transition probabilities. So you may hope that you can use this to derive some equations for the transition probabilities, and in fact that works. So the theorem is the following. The theorem is that if you look at this function, I guess I didn't define, here's the function. So if I look at this one-point distribution, okay, at time t, point x to be below r, and this is with general initial condition, okay, any upper semi-continuous initial condition h0, then this thing satisfies the 2D Toda equation, okay, written here. Again, above this point. That's the technicality. Okay? So this actually, this is, again, we proved it from these formulas. In this version, it sort of goes back to an old paper by Byhard and Pop, who did this in a sort of in an abstract setting and derived such formulas in a different, maybe in a slightly different language. But this is what you get for general initial conditions. Maybe I can say that in the flat case, there's no dependence on x anymore, okay, because the process is translation invariant and the initial condition in translation invariant. So you can drop x from this equation, and if you do this change of variables, you get that this function, which is now a function of t and r, satisfies the classic Toda lattice equation. Okay, so here this is the connection with Toda. Actually, there's a connection also. It's a little bit more complicated to write in the multipoint case. Okay, so let me show you quickly. Now I look at this multipoint distribution function, and I introduce this derivative. So I have a derivative in time, it's just in time, and then there's derivatives in x and r, and they're just sums of the derivatives in each of the variables. And you can go through, okay, now the proof is not the same as it's a more complicated proof, but still it's just computational if you want. And what you get is the following. You get that there's a certain matrix which is made out of the kernel, okay, such that the following two things are true. So number one, you can recover these ratios of the distribution as the determinant of this function. And the function satisfies something called the non-abelian 2D Toda equation. So it's a non-abelian version of the Toda equation showed before. It's written here, but this is integrable. It has appeared in different forms in these works. Okay? So again, there's this function. You just solve the 2D Toda equation and compute the determinant, and that gives you back these ratios.
Yeah.
Yes?
Can either this slide or the previous one be used to numerically compute the probabilities?
I guess so.
You haven't tried.
I haven't tried. Okay, there's, yeah, I have actually never thought of trying. There's one important problem, which is initial conditions, which I'm not saying here. So initial conditions here are not very nice. In particular, we don't know that these things are well posed. So we don't have uniqueness for any of these. Okay, so I'm just saying, okay, but anyway, if I want to do it numerically, I don't need any well posedness, but I need to make sense of the initial condition. My guess is that it should be doable, especially in the one-point case. The multi-point case, the initial condition is annoying. So, but in the one-point case, you can write it down nicely, and yeah, it should work.
I was more hopeful of the previous slide when you had this is numerically solved.
Yeah, I think it should be. I mean, and everything is completely determined, so yes.
You still need initial condition.
Yeah, but the initial condition is, okay. So it involves some minus infinities and stuff like that, but probably you can be clever and do it numerically and forget about that. The other one is a little bit more complicated because you have this matrix Q, and the matrix Q is not really physical. It's made out of this kernel that I was showing. And computing, and you need boundary conditions. It's not only initial conditions, you need boundary conditions because this thing starts at this deterministic evolution. That's a little bit annoying. So, but yeah, in the one-point case, it should work. Okay, I have 1 minute left, so I'll use it to just very briefly talk about KPZ universality. So, okay, so PNG is, if you want, expected or actually shown to be in the KPZ universality class. And what that means is that if you rescale this height function with this usual 1, 2, 3 scaling, it should converge to this universal limit called the KPZ fixed point. Okay? So in particular, this is just you can think of it, if you haven't seen these things, as a generalization of the area 2 and area 1 results that I showed you before. But now this would give you the evolution in time, and also it would work for general initial condition. Okay? So actually this can be proved using the Fredholm determinant formula that I showed you. It can also be proved in a completely different way using, which are it's more related to this last passage percolation version, using results of Duvernay and Virac. Okay, so I have this convergence, and now it's reasonable to wonder what happens if I take my Toda equations and I rescale them in this way. Okay, because I have a limit, so these distribution functions may also have a limit, and the answer you get is the following. So indeed, this can be done, at least formally. Okay, this is doing it rigorously is a little bit complicated, and there's not really much point. But when you scale these Toda lattice equations in the right way, and you expand everything, and you have to go up to fifth order, at the fifth order, everything, basically you just introduce the scaling, you expand everything in powers of epsilon, everything cancels up to fourth order, you go to fifth order, and what appears is just the KP equation. Okay? And in the multipoint case, really what's appearing is a non-abelian version of this is the matrix KP equation, and everything is analogous. Okay, so that's what you get in the limit. So this is formal, and I don't think I would have the energy to try to do it rigorously. In any case, this is known. So for the limiting process, it's known. So we had proved that a little bit earlier, that these one-point distributions or multi-point distributions satisfy either, in the one-point case, it's just the KP2 equation, just the scalar version. And in the multi-point case, you get this matrix KP equation. Okay, so I'm going to stop there, and thanks for listening.